should we even care about polymers in the first place? The plastics or polymers industry is estimated to be about $500 billion industry in the US alone. And at the heart of this industry are individual polymers whose properties can be designed or manipulated to achieve some bulk macroscopic behavior. And these polymers are typically manipulated in processes that involve things like injection mold, which is used for making materials like your automobile dashboard, the plastic extrusion, which is used for making materials like pipes and tubing, and the melt spinner, which is used for making things like nylon. But ultimately, these materials, even though they have a particular bulk behavior, their bulk behavior is determined by their equilibrium properties. But all the processes that I've described here are are not at equilibrium, and these processes typically involve a flow situation. So because the bulk properties that we see is a function of the equilibrium property, it's important to understand at the most fundamental level what the equilibrium properties of these materials are. So how do people typically determine what equilibrium properties are? So people do single molecule measurements where they tether a polymer chain, in this case DNA, to some active conservative field. And this field can be optical in nature, so like an optical tweezers where a bead is tethered to the polymer and this bead is being controlled by a laser, or a bead being controlled by magnetic tweezers, or in case where you have a cantilever that directly manipulates the chain. But the issue with this process is it doesn't really correspond to the situation that you see in processing, which involves flow. And secondly, you have all these really big probes on these molecules that are not necessarily indicative of the properties of the polymer chain by itself. So because of these issues, we sought to determine a new approach to determine these equilibrium properties. And basically, we use a device that generates flow fields similar to what you see in industry to deform your polymer chains under flow. And based on the molecular stretching trajectories, we can apply a non-equilibrium work relationship named the Jarzynski equality to get the equilibrium materials properties. So what is a non-equilibrium work relation? Well, a non-equilibrium work relation refers to a general class of work relations that allows you to determine properties at steady state or at some final state based on fluctuations or work distributions. The Jarzynski equality is arguably the most popular one, and it allows you to determine equilibrium free energy differences from work distributions. And to illustrate this, I have a picture of a Maxwell demon doing work in transitioning the system from state 1 to state 2. State 1 refers to a slightly disordered system, and state 2 is more ordered. Now, this demon can do this work at different rates. If the demon does the work at a slow enough rate, the average work done by the demon is equal to free energy change. But if it does it at a finite rate, then there are irreversibilities in the process, and your average work is not necessarily equal to your free energy change. Well, the good thing about Jarzynski's equality is that it's valid regardless of the rate at which you do the process or how far you are from equilibrium. Now, since the equality has been derived, it's been applied extensively in the field of biophysics with over 1,500 citations, but it hasn't really been applied to soft materials or polymer dynamics. Another class of non-equilibrium work relations is Crookes fluctuation theorem. I wouldn't really go into this in the interest of time, but I'll be happy to answer questions about it later. So what does Jarzynski's equality look like? Well, it relates to an exponential average of a Boltzmann-weighted work to the free energy change. And this equation is valid in the limit of infinite ensemble. It's true regardless of your deformation rate. And so since it's been developed, it's been applied mainly in the where your system is being deformed by conservative forces. There have been some cool experiments and computational work that have shown that this equality is valid in different cases. But because we want to use this equality to study polymer dynamics and determine equilibrium properties, we need to figure out a way to capture the physics of polymer dynamics. And to do this, we have a very simple model for polymer dynamics, a coarse-grained model where we model a polymer as beads connected on a spring. The beads serve as contact points with the fluid, and the spring represents the effective elasticity in the chain. Now, this polymer is typically stretched in flow fields, and I have two example flow fields here. You can have an extensional flow where your polymer chain is in a strongly stretched regime, and kappa is the velocity gradient tensor describing the flow field, and you can have shear flow. Now, the equations describing the behavior of this polymer in flow is given by a Fokker-Planck equation for the configuration distribution function. But for the case of our simulations, we want to solve the equivalent stochastic differential equation to model the behavior of the polymer in flow. And the key ingredients that go into this system is the flow velocity, or the fluid flow, which is responsible for driving the process, the diffusion tensor, which describes the mobility of the chain, the elasticity, which describes the properties of the chain, and also the Wiener process, which is descriptive of thermal motion and fluctuations. So we know how to model the system. To apply Jarzynski's equality, we need to determine what the work is. So we did some theory by using equality known as the Tano-Sassa equality, and we're able to determine what the work definition is for polymeric systems. And based on this work definition, we can apply this expression, which is just the Jarzynski's equality, in flow. So we can now use our simulations to test our expression and Jarzynski's equality. So what we do is that we transition a polymer chain from a particular extension to a higher extension by increasing a particular flow, the flow rate. And you repeat this process a bunch of times to get a work distribution. And based on each trajectory, you have a particular distribution. So the black line here shows the average molecular stretch as a function of time. So based on this individual distribution and the equation above, we can actually compute what the work distribution is and apply Jarzynski's equality. And what we see by applying Jarzynski's equality is that we can determine what the equilibrium free energy change is to within 1 kT of what the analytic value would be. We find that this is remarkable because although you have a really large dissipated amount of work, almost 120 kT, you can still determine what the equilibrium free energy change is. So we've done this in a bunch of flows, extensional flow, tele-uniform flow, and by increasing the velocity over time, you can actually map out the entire free energy landscape of your molecule. So after determining the free energy landscape of a molecule, we can go ahead and determine the elasticity by taking a derivative of your free energy with respect to extension. And by doing that, we can actually determine what the elasticities in the chain is from dynamic flow data. We've done this not only for biopolymers like double-stranded DNA, but we've also done it for synthetic polymers like polystyrene. But the results I've shown you so far have been results of the idealized case. So a case where you have your polymer represented by two beads and where the diffusion tensor is constant. But in reality, we know that the diffusion tensor is not always constant, and for us to transition into an experimental framework, we want to capture the physics entirely. So we put in the case, we also decided to consider the case where your diffusion tensor is no longer constant to test a framework to see if it works. And it does work. Although the equations of motion are slightly different because you have multiplicative stochasticity because of the diffusion tensor varying with the configuration of the chain, you can actually go ahead and calculate what the equilibrium free energy landscape of the molecule is from flow data. So we're pleased with this, and this motivated us to go ahead and consider test this framework in an actual experiment or experimental data. So we obtained previously published experimental data of polymer molecules, imaged using single molecule fluorescence microscopy in extensional flow. And based on the stretching trajectory, and our previous equations for the work, we can actually derive what the work done on the molecule is in different regimes of the chain. We note that the polymer chain transitions from a coiled state, where it behaves like an effective sphere, to a slender state. We have an image here showing that, where it behaves like a slender body. So by using this definition, we can actually determine what the work done on the chain by the fluid is. So using this work expressions, and applying Jarzynski's equality, we went ahead and to determine what the free energy landscape of the molecule is. And by using our approach, we can actually determine the free energy landscape despite the huge amount of dissipator work from flow data. And I was pretty shocked by the result, I must say, because the simulations typically required a larger number of trajectories for convergence to the free energy landscape. But in reality, in the experiment, you have a more realistic system, so you typically require a lower number of molecules to determine the free energy. So in conclusion, I hope that I've convinced you that non-equilibrium work relations can be applied to polymer systems and can be used to determine equilibrium properties from highly non-equilibrium flows. And based on this equilibrium properties, we can determine the stored elastic energy and the elasticity in the chain. Thank you.
Any questions? So, Bob, thank you.
All right.
And this concludes this session. We have a small break now. We have the poster session in this room outside.